Hi everyone, we are from group number 7. I'm Herman, and our final project topic is detection of COVID-19 from X-ray images. Our agenda is pretty simple. I will talk about problem statement and initial data preparation. And our project goal is we want to build a CNN-based deep learning model that is able to distinguish positive cases from negative ones from patients' lung X-ray images. So we have 3 data sources. First is Brixia, NIH, and COVID-10GR. Basically, we have an imbalanced data set as the positive trend cases is around 4,700 X-ray images, while the negative trend cases is like 100,000 X-ray images. With that, I will transfer to Jinyu to talk about data preprocessing and EDA visualization. Thank you.
This is Jinyu. We visualize original images from the datasets. We can see from the images and their histograms that they vary in brightness, contrast, shape, noise level, and orientation. So we need to prepare the data before training. The first technique we use is the color filter. It enhances the contrast of the images and makes the infected areas more distinguishable. We also apply data augmentation to provide more robustness to the model. This is important for positive cases as well because it reduces data imbalance issue. The data shown on the left are the ones after process. They become more suitable for training. The red shows that we also attempted to extract the features of the data by shifting the pixel values distributions. But the result is actually not satisfactory enough due to time and computational power limitation, so they are actually not used in training the model, but for understanding the data.
Given the data complexity, we further categorized 4,700 positive training data into 4 subgroups based on modality and projection. Negative training data is about 3 times more than positive training data, and it is further categorized into 21 subgroups based on medical condition. And the first model we explored was simple CNN because it's easy to adapt and it provides intermediate outputs to detect the COVID features and was fast and efficient in changing architecture.
In this project, we use by most CNN binary CNN category with GG16, dense-NAT 121, and race-NAT 50. The parameters, of course, is model are very similar. We use them as the optimizer for most modes, except with GG16, we use XGT. The learning rate was set to 1E -5 for more modes, except the race NAT 50, which was set to 1E -3 due to the slow processing speed of our device, which significantly extend the running time. Since the data set is significant imbalance, we use signal focal cross entropy as a loss function. The batch size was set to 64 for all modes, and the epochs we set 30 for the CNs and reduced to 10 for the pre-trained modes. We apply a dropout rate at 0.3 and a batch normalization for all modes. The matrix monitors, including accuracy, precision, recall, AUC to positive and to negative. Training time costs 80 minutes for the CNN modes and 2 to 3 hours for the pre-trained modes. Here's the training summary for the CNN binary mode and the CNN category mode. That was a result from the CNN mode. And that was a result from the GG16, and the result for the dense-NAT 121, and the result for the RS-NAT 50.
Hi, this is Paul, and I'd like to go through the results of our project. First, on the training and validation results, if we look at the validation accuracies, we can see that the pre-trained models did much better than our own models. However, if we look at the test results, you can see here that all model accuracies were only around 50%, and average F1 scores are also similarly bad. Now, the question is why? And we believe the biggest reason is our test data. That is non-representative. We tried different image standardization and enhancement techniques, and no model was able to do well. And we actually tried our model on other publicly available data set, and we got more than 70% accuracy. So we know that the test data that we were given was the biggest challenge. So in terms of our conclusion, we learned from this project how important data processing really is versus just trying fancier and fancier models, which is what we did. In terms of practical impact, we should research more on image quality, standardization, and enhancement techniques in the future. Finally, in terms of future work, we would like to do more work on data processing, and we believe utilizing data distribution analysis could be the key. And finally, last resort, we'll try also more complex models in the future. And thank you so much for listening. Thank you.